Hello and welcome. Today we're going to be looking at the unit test for Introduction to Energy, one of the topics in physics, both honors and standard. As always, we're going to be going through all 9 of these questions on this unit test to make sure that you understand how to approach and solve these kinds of questions. If you like these videos, please be sure to like and subscribe. And with that, let's get started on our first question. Here we go. The diagrams below represent the motion of the molecules of a gas. Each container holds the same type of gas and has the same volume. The length of each arrow is proportional to the speed of each molecule. So the following correctly describes the thermal energy. Okay, let's see. Lowest in container A, because molecules in this container have less space to move. Well, that's not true because they all have the same space to move. B is the same in containers B and C because these containers have the same number of molecules. Doesn't seem correct, but it is the same in all 3 containers because each container contains the same substance. And then it is lower in container C because container C contains the fewest molecules at the lowest speed. Okay. What do we have here? So it's not A. Answer choice A is incorrect. Answer choice B, the same number of molecules. Well, that doesn't really determine the thermal energy, so that is going to be incorrect. Same in all 3 containers because each container contains the same substance. Well, that doesn't seem correct either because if you just double the number of molecules, you're probably going to increase the thermal energy. Lowest container C, fewest molecules, lowest speed. That seems correct. And we can move on to the next question. How does the mechanical energy of the car at point B compare to that of the car at point C? Let's see. So, assume friction is negligible, right? So if we're assuming friction is negligible, then mechanical energy is generally not going to change. You're just going to have it transferred from a lot of kinetic energy and low potential energy to low kinetic energy and zero kinetic energy technically, and a lot of potential energy. So there's no change. No change. You're just changing what type of energy it is, but you're not like getting rid of mechanical energy at all. So it's the same because energy is conserved during the motion. Let's keep going. Students are expelling an electric charge using 2 negatively charged foam plates. Students rub the plates with a wool cloth to add additional negative charge to both plates without changing the plates' positions. The plates are interacting through an electric field. How does the energy stored in the field change after the plates become more charged? If you increase the charge, well, charge is proportional to energy, so if you increase the charge, the energy is going to go up. See, potential energy in the field is going to increase. And we can keep going to the next question. Students observe their teacher mixing nitrogen and hydrogen gas in a jar to obtain ammonia. Nitrogen gas plus 3 hydrogen gas equals 2 ammonia. The teacher allows them to touch the jar before and after the reaction. The students notice that the jar is warmer afterwards. Okay. The following cause the increase in thermal energy. Let's see. So what does this mean? This means that the reaction up here is going to be called exothermic. Right, this is using chemistry language. If you haven't taken chemistry, don't worry about it. But this is exothermic, meaning that it's going to release energy. That was a horrible C at the end. It means it's going to release energy. Okay, so how does that work? Well, energy is released when you form bonds. Right? Energy is released when you form bonds. Okay, so we have two nitrogens and then like hydrogen times 3, and you're ending up with like this. I know this is not a chemistry class, so it doesn't really matter how you draw it out or anything. Times 2. But the point here, right? The point is that you have exothermic reactions. You release energy when you form bonds. So you're causing an increase in thermal energy. So there has to be a decrease in something else, and some other energy, which is going to be energy stored in molecular bonds, or the decrease in electrical potential energy stored in those molecular bonds. Let's keep going to the next question. 2 roommates are sitting in their living room on a hot summer afternoon. One of them plugs a fan into a wall socket and turns it on. Which forms of energy are most involved in the operation of the fan? Well, you're getting electrical energy to the fan, and then the fan is turning, using that as kinetic energy. So it's going to be electrical and kinetic energy. Let's keep going. Carl uses energy from a fully charged battery pack to light up a high-efficiency light bulb, which converts about 80% of its electrical energy into light. After an hour, the battery pack is no longer full. He also noticed that the temperature of the air near the light bulb has risen slightly. Okay. Up to the energy of the battery pack. Well, 80% of it, 80% of it is the light that you get from a light bulb, because obviously. The other 20% can probably do something like thermal energy, like heat. How do we know? Well, there has to be heat energy somewhere, because we're told that the temperature has risen slightly, so we know that some of it transferred into heat, into thermal energy. So most of it transferred into light energy, 80% light energy, and a small portion transformed into thermal energy. All right, you can't just like small portion disappear. That's not how it works. And the other two don't say that most of it became light energy. All right, let's keep going. In his first soccer game of the season, George kicks the ball towards the goal, but the other team's goalie catches it out of the air. Which of the following doesn't describe an energy transfer in the scenario? Well, let's see. It says the ball transfers kinetic energy to the goalie. The ball transfers gravitational potential energy to George. The goalie transfers kinetic energy to George, and George transfers kinetic energy to the goalie. So the first thing I'm going to mention is the fact that George is kicking the ball. Okay, so George kicks the ball, transferring kinetic energy to the ball. And then the goalie catches the ball. So the ball's kinetic energy transfers kinetic energy to the goalie. Okay, so let's see. So there's no kinetic energy going to George, and there's no gravitational potential energy. So these two are incorrect. These two are incorrect. Right, now we have two options. The ball transfers kinetic energy to the goalie, and George transfers kinetic energy to the goalie. Well, let's think about this. Alright, so we could technically make an argument for George transferring kinetic energy to the goalie, because he's transferring kinetic energy to the ball, and the ball is transferring kinetic energy to the goalie. But in that, the ball is also transferring kinetic energy. And I think it's very important that we realize that kinetic energy is a force that can only be transferred by contact. It's a contact force. Right? You can't transfer kinetic energy without having contact. Alright, if you're not touching something, you're not going to transfer any kinetic energy to it. Alright, so you have to touch it. George and the goalie aren't in contact, so the answer is going to be choice A. And we can move on to the next question. There is an attractive gravitational force between two planets that are moving through space. The two planets interact through a gravitational field. As the two planets move closer together, how does the energy stored in the gravitational field change? Well, remember that the energy in a gravitational field, gravitational potential energy, is going to be the mass times the gravitational times g, the force, times the height, the distance between them. As the distance increases, the energy increases. They're moving closer together, so the distance decreases, so the energy in the field is going to decrease. Energy in the field decreases. Let's keep going. Which of the following statements are true about chemical energy? Chemical energy is a macroscopic form of energy that we can model and measure. Chemical energy is a form of energy that individual atoms have. At the microscopic scale, chemical energy can be understood as the energy that atoms have due to their positions. Alright, let's see. What do we have here? Okay. Let's think. Okay, so chemical energy. What is chemical energy? Chemical energy is a kind of macroscopic form of electrical potential energy. It's really just electrical potential energy scaled down because it's the energy between bonds, energy stored in those bonds. So it's not going to be a form of energy that individual atoms have because it's stored in the bonds. At the microscopic scale, chemical energy can be understood as the energy that atoms have due to their positions. Well, atoms do their positions, right? It's stored in the bonds. The bonds is what contains chemical energy, not the atoms. So atoms don't have chemical energy. The bonds have stored chemical energy. So this is also going to be incorrect, and our answer is going to be choice A. Chemical energy is a macroscopic form of energy, of electrical potential energy, so it's going to be macroscopic. And we can model and measure it through the number of bonds, through the strength of bonds. Right? If you take a chemistry class, you'll have extensive practice in dealing with what we talked about before, right? Exothermic, endothermic. You'll deal with enthalpy. You'll deal with entropy. Those kinds of things are measures of what goes on in the chemical energy in those bonds. Right? We can actually model and we can actually measure. We know how much energy is stored in those bonds. Right? If you take chemistry class, you will learn all about that. But chemical energy, we can model and measure it. That is our answer. We are going with choice A. And we're done. Alright, so that was the unit test for Introduction to Energy, one of the topics in physics. I hope you enjoyed this video or learned something from it, and I'll see you next time we continue looking at more topics in physics. I'll see you then.